Hi guys, welcome to the Gramolly YouTube channel, and in this video I'll be continuing from my last lecture on Lagrangian mechanics where I discussed when, where, why the Lagrange is used, and we went through a few practice problems to gain more understanding on how to solve such problems. So I would recommend you to watch that video before watching this one. So today first I'll be solving an instructive example problem, then I'll be going into the core of Lagrangian mechanics, which is the principle of stationary action. After that, I'll be using calculus of variation to solve various minimizing problems, and I would suggest you to keep a lookout for that. So here we go. This is the first practice problem. We have a homogeneous rod of length L, cross-sectional area A and mass m which floats in water. Density of water is given to be rho. It is connected by a spring with spring constant K, which is in turn connected to a rod resting on its center of mass. Okay, the rod has the same mass as the wood and is twice as long. So if this is L, this is 2L, and the wood can only move horizontally. Okay, the spring is in its lateral length, so initially the potential energy of the spring is 0. The acceleration due to gravity is g. It oscillates harmonically with the vertical displacement of wood, and the rod angle deviation assume it to be very small. So we probably have to do some sort of small angle approximation. So first he is asking the equation that expresses the equilibrium state of system. That isn't too hard, as that would just be the buoyancy force equal to mg, as initially it is in its natural length, so there wouldn't be any spring force acting. The potential energy of the spring in terms of g, k, rho and theta, and the kinetic energy in terms of m, x dot, l and theta dot, and the frequency of oscillation he's asking. So this problem is crying out loud to use Lagrange. It told, right, the potential energy of the system, right, the kinetic energy of the system. It's just crying out loud, use Lagrange and solve me. So let us solve using that, and then we have to analyze this result from part D in limiting cases of k tends to 0 and k tends to infinity. So let's proceed with part A. Part A is nothing but just Fa is nothing but the buoyancy force is nothing but equal to mg, and the part that is submerged is nothing but L minus h minus x naught. So L minus h plus x naught. So it is L minus h minus x naught, which gives this. So Fa equal to mg, which is nothing but this is the buoyancy force, Archimedes principle. You get m is nothing but rho a into L minus h plus x naught. So that is the equilibrium position. Now say it is displaced from its equilibrium position by a distance x. So it's new x is, say, x of t. X naught minus xt would be nothing but L naught minus x. That is evident from the picture here, as L naught plus xt minus x is nothing but x naught, implies xt minus x naught is nothing but L naught minus x. Okay, so the potential energy stored in the spring is half k delta x square, which is nothing but half k L square theta square minus 2L theta x plus x square. So just square this, you get this, and then the gravitational potential energy is nothing but minus mgx. Assuming this to be a reference, it has fallen a distance x, so the gravitational potential energy would be minus mgx, and the potential energy of the water, so the buoyancy force is nothing but rho g a L minus h plus x naught plus x. That is the force. Now we all know that potential energy is defined as minus f dx, change in potential energy. So that is what I am essentially writing here. I am integrating from 0 to x, as initially it was at its equilibrium position. So that just gives us minus rho g a L minus h plus x naught plus h cos pi, as the directions are opposite. The force is upward and the displacement is downward. Okay, so we have got the V of the water as well, and then we have got the V of spring, V of gravitation and V of air. Adding them all together, we get the total potential energy of the system to be half k L square theta square minus 2L theta x plus x square plus half rho g a x square. That would be the total potential energy of the system. Now the total kinetic energy is just the rotational kinetic energy of the upper rod and then the translational kinetic energy of the wood block. The rotational kinetic energy is nothing but half I omega square, and then for wood it's nothing but half mv square. That's what I've written here. So that would be the total kinetic energy. Now you write the Lagrange. You get this to be the Lagrange. 1 by 6 ml square theta dot square plus half m x dot square minus half k L square theta square minus 2L theta x plus x square minus half rho g a x square. So parts A to C are done. We are applying the Lagrange right now. I'm trying to find omega. So there are two variables here, x theta and x. The only way to solve this problem would be applying the Lagrange twice, because if you apply it only once, you won't have enough equations to solve the system of equations that you get from solving the Lagrangian. So first let us write the Euler-lagrange for x and then the Euler-lagrange for theta. I am sparing you the calculation. You get dou L by dou x is nothing but KL theta minus KX plus rho g AX, and then dou L by dou x dot is nothing but MX dot. So d by dt of dou L by dou x dot is nothing but MX double dot. Now similarly you get dou L by dou theta as KLX minus KL square theta, and dou L by dou theta is nothing but 1 by 3 ml square theta dot, and differentiate this again with respect to time. You get 1 by 3 ml square theta double dot. So we have 4 equations, 1, 2, 3, 4, and we have 4 unknowns. Assuming theta dot all to be independent, you get this. We have 4 variables here, but 3 and 4 combined gives us 1 equation, 1 and 2 combined gives us 1 equation. So we have 2 equations, 4 variables. How do we solve this now? The thing we have to use is, as he had mentioned in the problem, we have to assume the rod, everything to be moving simple harmonically. So we can just assume a solution theta double dot of a form minus omega square theta and x double dot of a form minus omega square x. These were the two Euler-Lagrange equations that we got, mx double dot minus kl theta plus k plus rho g ax equal to 0. Similarly, we get for theta double dot. Now substituting this back in, we get a slightly bad looking equation, k plus rho g a minus m omega square x minus kl theta equal to 0, minus 3klx plus 3kl square minus ml square omega square theta is 0. So we got 2 equations here. Now we get x by theta in both, equate both the x by thetas, and you get k plus rho g a minus m omega square into 3kl minus ml square omega square equal to 3k square L square. This is clearly a quadratic equation. On solving, I just want to spare you the calculation. It's not pretty. You get the frequency to be 1 by 2 pi square root 4k plus rho g a plus minus you get. So there are 2 possible frequencies, assuming this whole thing to be positive, which it might not be. If it is not, then only one will be accepted. So we get 4k plus rho g a plus minus 16k square minus 4k rho g a plus rho g a square. As k tends to 0, this becomes 0, this becomes 0, this becomes also 0. So rho g a plus minus rho g a. So it is either 2 rho g a by 2m or 0. So either the frequency is 1 by 2 pi root rho g a by m, which is the same as massless inelastic rod. And the first equation significance is that physical significance is that it gives you the same frequency as if they were oscillating simultaneously in opposite directions. Okay, so let us now discuss the principle of stationary action. Let us define quantity S as the action, which is nothing but integral of the Lagrange, which is a function of x dot t dt from t1 to t2. That would be the definition of quantity S, which I am defining as the action. This is not an arbitrary definition. There is a good reason for it, as you will see soon. So my claim is, if the function x naught of t gives a stationary value of s, that is it is either a local minima or local maxima or a saddle point, then you essentially get back the Euler-Lagrange equation, provided the endpoints are fixed. Prove that the function x naught t that gives a stationary value of s obeys the Euler-Lagrange equation. That is my claim. Now we have to prove it. Say a function x naught t yield the stationary value, then a function x1 t very close to x naught. So say this is x naught t, then something very close to it also must yield the stationary value with a maximum of a first order deviation. This is evident from the Taylor series expansion, and I would not like to go into that, but this is clearly evident from. So say I define x1 t as x naught t plus c f of t, where c and f of t are two arbitrary functions with only one condition on f of t, that is the endpoints f of t1 and f of t2 must be 0, as the endpoints for all functions must be same. So if it is non-zero at t1 and t2, then x1 of t1 would be unequal to x naught of t1, and the endpoints would not be same, which is violating our initial condition. Okay, so what do? We differentiate the action s of x1 t. So I'm writing the action in terms of x1 t. You just get dou L by dou C dt. That would be the action. Now, since you integrated, you can just take the dou by dou C inside. Now I'm applying the chain. I'm applying chain rule. Dou L by dou x1 into dou x1 by dou C plus dou L by dou x1 dot into dou x1 dot by dou C. Now dou x1 by dou C is nothing but f of t, and then dou x dot by dou C is nothing but f dot t. That is evident from this equation. You differentiate it with respect to C, and you just get, you partial derivate it with respect to C, and you just get f of t, and then you differentiate it again with respect to time, you get f dash t. So now, since we know the value of dou x1 by dou C and dou x1 dot by dou C, we can put that back into this expression, and we get dou L by dou x1 f plus dou L by dou x1 f dot dt as our expression for the partial derivative of the action. The second part can be differentiated using chain rule. The second part can be integrated using chain rule. Let us cheekily apply it here. We integrate this, we get f dou L by dou x1 dot, and then we differentiate the other part, dou L by dou x1 dot into f dt. So I have applied integration by parts here, and since f of t2 equal to f of t1 equal to 0, at the extrema this is 0, hence 0 minus 0 is 0, so this has to be neglected, and so this has to be 0, and hence we just get dou by dou C of s of x1 t is nothing but dou L by dou x1 minus d by dt of dou L by dou x1 dot into f dt. So this must be true for whatever function f. So whatever function f, this must be 0, and that is only possible if the term inside is also 0, because for all values of f, if this total thing must be 0, then the thing inside must also be 0. And this is because we are assuming at x naught of t there is a stationary value. So instead of x1, I am writing x naught here, because at x naught only there is a stationary value. So at x naught, the thing inside the bracket, it must be 0. That gives us dou L by dou x naught equal to d by dt of dou L by dou x dot, which is the same thing as the Euler-Lagrange equations. Now let us discuss the principle of stationary action. So I make another claim where I say a particle always follows the path in that yields a stationary value of the action. that so the stationary value of action has been defined in my previous claim. So I am telling, if and only if the action for which the path that follows is stationary, then only the particle would take that path. So that this seems like a far-fetched claim, and you might ask me to prove it, but the proof is very ingenious. So in my last video I had proved the Lagrange is same as f equal to ma in 3D coordinate system. It can be proved in any coordinate system, but let us assume 3D coordinate system for now. Path yields the stationary value of the function. It implies that it is equivalent to Euler-Lagrange equation, which is equivalent to f equal to ma, which means that if f equal to ma is valid, this is also valid. Since we are assuming f equal to ma is valid, this must also be valid. So what are the applications of what we have just learned? I'm glad you asked, because there are some extremely crucial applications for this in calculus of variations. So the first problem we are going to tackle, from which you will understand how powerful this is. We have to prove that the shortest distance between 2 points is a straight line. How do we prove that? Till now, whether you have noticed it or not, you have probably assumed it to be true. In ray optics or whatever, you have probably assumed it to be true. So today I'll be proving this using our newfound principle of stationary action. So say the path between two functions is given by some function y of x. Now the derivative of that, so say I take a very small portion of it. The derivative of that will be theta. So tan theta is nothing but y dash x. So the total length would be 1 plus y dash square of that small region by dx. So to get the total length, you'll have to integrate it over dx from x1 to x2. That would be the total length. Now for few of you might have instantly noticed the similarity with action. You have to minimize, say L is some action here, you have to minimize L here. So can you find the clear similarity between this and the principle of stationary action, where we just defined a function this and we try to minimize, maximize, or give it a saddle point? So yeah, so that is essentially what we are doing here. So this would become the Lagrange, and instead of t it is x. That's it. That's the only difference for the action here. So the Lagrange is nothing but root 1 plus y dash square. Now since the variable is x, you have to differentiate with respect to x of dou L by dou y dash and equate it to dou L by dou y. On solving this, you get d by dx of y dash of root 1 plus y square equal to 0, which means this is constant, which means y dash must be constant, i.e. the slope must be constant, hence it must be a straight line. If the length must be minimized, it must be a straight line. So the shortest distance between 2 points must be a straight line. It can't be any other curve. If it is any other curve, the path length would be higher, as it would not be satisfying the Euler-Lagrange equations. Yeah, so this is a very important application of the Euler-Lagrange equations, because we normally do not prove that the shortest path between 2 points is a straight line, and we take it for granted, whereas there is some beautiful physics involved behind it. We are using x instead of t and our variable is y. So we apply Euler-Lagrange again and we get 1 plus y dash square is b by y square. I am sparing you the calculation, it's pretty simple calculation. We get x minus x dash square plus y square is b square, which is the equation of a circle. Surprisingly, maybe not surprisingly, the light must travel in some circular arcs inside the slab. So yeah, so this seems very interesting, right? You can of course solve it with Snell's law, but the problem specifically told you can only use the fact that light takes minimum time. So I think you're getting the hang of how beautiful Lagrangian mechanics is. So yeah, we'll be solving more and more examples on this. First, I'll be taking a lemma here. This would be very useful for any kind of minimizing time, minimizing length, whatever problem. I'm just stating it here. It's very easy to prove it yourself. Say we need to extremize, not minimize, maximize, either minimize or maximize the integral f of y square root 1 plus y dash square dx. So that's basically what we got before. We got 1 by y once, we just got f of y is 1 once. So f of y is any arbitrary function, but it is a given function. Then to solve for y, we have to get the equation 1 plus y dash square is nothing but b f of y square. So it is, yeah, so it is f of y whole square. So 1 plus y dash square is nothing but b f of y whole square. So you prove this on your own, but I'm going to be using this as it is very useful for any kind of minimizing time, minimizing length problem. Yeah, so let us solve a little different kind of a Lagrange, though it is essentially the same thing. So we have a membrane of water that is stretched between two parallel rings. What would be the shape of this membrane? So this is a water membrane essentially. So it is in a around the whole ring in some sort of a cylindrical manner with increasing radius like this. So you are essentially asking for the shape of this, and the two radii are given and the x1 x2 are given. To solve this problem, the fact we need is that water always tries to minimize its area due to surface tension. So we need to find the shape for which the area of this, the lateral surface area is minimum. Sorry, the curved surface area is minimum. So let us slice this into small vertical rings, each of area 2 pi y square root 1 plus y square. So that would be 2 pi y would be its circumference and root 1 plus y dash square would be the distance. So that the total area would just be 2 pi y root 1 plus y square dx. That would be the total area, and we define this to be the action. This would be our Lagrange. Our Lagrange is nothing but 2 pi y root 1 plus y square. We can always just ignore the constant. It is somewhere in b. Nobody cares about the constant. Directly straight up, the f of y is nothing but y. 1 plus y dash square is by square. Just solve this. You can solve this on your own. Write it as dy by dx and you solve it. You get 1 by root b cos h root b x plus d. B and d are constants that we introduce while solving the problem, and they can be found by applying the boundary conditions where y of x1 is r1 and y of x2 is r2. So the next problem is we have to analyze this case where both the rings have the same radius and the distance between the rings is L. This is a standard surface tension problem, but people use a direct result. You should not be using that. It's a beautiful problem. From boundary conditions, we just get BR is nothing but cos h BL. From the past problem, we can just substitute the values and we get BR equal to cos h of BL. And cos h is the hyperbolic cosine. It's just a way of writing e powers in a concise way. Look it up if you don't know. It would be helpful to write stuff in a small manner, and it gives more beautiful looking answers, though in fact they aren't. Okay, so I'm going to be defining two new variables here, eta, which is nothing but the ratio of L and R, and Z equal to BR. So essentially what I have to find in this problem is the maximum ratio L by R for which this is stable and it doesn't break. So substituting this back in, I just get Z is cos h eta Z, which is so now solving this is a little hard, Solving this is a little hard. The way we can think of it is somehow saying x equal to cos h eta x, where eta is changing. So say this is one small value of eta, y equal to z and y equal to cos h eta z have more than one intersection points, and then there is a critical value theta for which this is tangent, and above this value of theta it no longer intersects, so there is no real solution z for which this happens. Hence it would become unstable as the Euler-Lagrange equations are not valid. So the minimum surface area, so there will not be a surface of minimum surface area. The membrane would just break and then go on the two rings separately. It would just break in the middle. So yeah, so it must be tangent for max theta, and above that there will be no solutions. So say it intersects at z0, and the value of n0 for, and the value of eta for which this happens is eta naught, and the place where it intersects is z0. Then we get z0 is nothing but cos h eta naught z0 as directly from this equation. But also, since it's tangent, the slopes must be same, and the slope of cos h is nothing but sin h and not eta and not z0. Cos h is nothing but sin h, so we also equate slopes to get 1 equal to eta naught sin h eta naught z0, and dividing both of them we just get eta naught z0 tan h eta naught z0 is 1. This has to be solved by Desmos or something, because it is pretty hard solving by hand. So I have solved it using Desmos, and you get L by R eta naught maximum value to be 0.663. So yeah, these are also another standard types of problems where they ask to minimize the area. They won't ask you directly, but you'll need to understand when to use this. Whenever water is involved, whenever surface tensions are involved, this is extremely useful, and make sure you have that lemma in mind so that a lot of time is saved during the exam, because this is a very famous thing and it can come anytime in any exam. Yeah, so okay, yeah, so let us now solve the Brachistochrone problem. You probably have seen from many videos of probably Vsauce or something, where they leave a bead from origin on some wire, any arbitrary wire, and you have to reach a point x0 y0. You have to optimize this wire such that it reaches it in the shortest time possible, and there is obviously gravity g downward. So this is straight up it is easily destroyed by our method used so far. Just T is ds by v. We have already used this in our Fermat problem. ds we have already got root 1 plus y dash square, and then v from conservation of energy root 2gy dx. So the Lagrange is nothing but square root 1 plus y dash square by root y, and substituting that into our lemma, we get 1 plus y dash square is b by y, and this can be easily solved by substituting y. We get, and from this we get square root y dy by root of b minus y is plus minus dx. This can be easily solved by substituting y equal to b sine square theta, and then on solving, I am leaving the calculations for you. We get x is nothing but a into theta minus sine theta, and y equal to a into 1 minus cos theta. So is this equation familiar? You might have seen this somewhere, though you are unable to recollect. Let me try to give you an idea. It's in rotation, so it's the path of cycloidal motion, the path followed by point on the rim of a wheel, rolling wheel. So it goes like this, like this. That was the cycloidal motion, which is even used in many magnetism problems. So yeah, always keep the cycloidal path in mind. It is a very famous path, and suddenly someone can ask you, prove that a bead follows a cycloidal path when moving from origin to x0 y0 in presence of a uniform accelerated field. In case you didn't know what a cycloid was, you would not have been able to answer, but it's a very standard curve and should always be kept in mind, and this is the parametric form of the curve. Just keep that in mind always. And yeah, so that is our lecture for today. We have covered quite a bit of material, lot of minimizing, maximizing, principle of least action, etc. So in the next video, whenever it is, I'll be continuing. I'll be going even deeper into Lagrange. And yeah, so thank you everyone for watching. It's been a pleasure.